In this video, we are going to talk about how to solve almost exact equations. So solving, let's call it almost exact equations, and it will be clear what we mean by almost exact in a minute. So let's consider let's say m x y dx plus n x y dy. So this is in a standard form, but it may be the case that so let's say it may be the case that we know the criteria for exact equations. What we try to do, we try to match the da by m over da by y with da by n over da by x, but it may be the case that they are not equal. So if they are not equal, because in general this is the case, so that means this is not exact. So not exact, that means we need a new criteria. So what we try to do, we try to do something similar to first order linear differential equations, the integrating factor method. So we try to use a similar idea here. So we're going to use the integrating factors. Okay, so we're going to use an integrating factor. But in this case it may be a function of x and y. So we write two variables. Actually later it can be seen that it's going to be only one variable, because that's the case we can solve here. Okay, that's the case we're trying to study. So now what we're going to do, so we just do the similar argument here. So let's suppose this is an exact equation now. So so what we're trying to do, we're going to multiply our original equation by that integrating factor. So that means we have I x y comma I x y m x y plus I x y n x y equal so actually we missed few things here. So we let's write the dx dy term as well. So we have times dx in the first one, dx plus I x y n x y dy equal 0. So let's say this is the case. So what we did, we multiply the original equation by integrating factor, and we can suppose that this is an exact equation. So suppose this is exact. So we can suppose this is exact equation, and we try to derive the condition. So if this is exact equation, what we know that the partial derivatives of the first one with respect to y equal the partial derivative with respect to x on the other side. So that means we can write da by over da by y, the I m product equals to the da by over da by x, the I n product, because it's a product now. Now what we can do, we can take the partial derivatives like this, just use the product rule, and then we try to derive the condition from this. So let's do that. Good. So then so what we had again, da by over da by y I m product equal da by over da by x I n product. So if you use the product rule, this is going to be I m y. This is the meaning the partial derivative. So we just put it like a small subscript, mean the partial derivative with respect to y. That's the other notation. And then here I y, that's a partial derivative with respect to y of I times m equal the same thing I n x plus I x n. So what we did, just use the exact same product rule, but instead of the regular derivative, now we have partial derivatives. That's the only difference. Now what we do, we're going to make a rearrangement of the terms. So we can write this one as ix n. So this is just one way to write it. Iy m equal my minus nx I. So now we're gonna make a interesting assumption for simplification purposes, because this is not true. Like what we're trying to assume is not true in general. So what we're gonna do, we're gonna say if the I function is a single variable function, that means a function of only x or function of only y, we can simplify this further. So let's say this. So we can say if I is a function of one variable. I is a function of one variable. So function of one variable. We may simplify. So let's talk about two cases. So I'm going to call type 1. So what's the type 1? So type 1 means, let's say if I is a function of x alone, if I is a function of x alone, so only a function of x, then what will happen? If I is a function of x alone, then the partial derivative with respect to y has to be 0. So that's the interesting case. So that means this term going to be 0. So that means that term gonna go away from the equation. Good. And then your equation becomes ix n equal my minus nx times I. So that means, so we simplify up to that, but we still don't know anything about my nx over n. So what we try to do, we have this, then we can write this one as ix equal, if you divide by n both sides, you're going to get my minus nx over n times I. Now we still don't know whether we can simplify this or not, we can solve for I or not, but we can have one more assumption. The other assumption is, what if this function is only a function of x? If this is only a function of x, then we can integrate, we can use the separation of variable method to integrate this one. So that's the next assumption we're going to make. We're going to assume that that part is only a function of x. That's only a function of x. So let's say if my minus nx over n is also, so it's another assumption, that's the second assumption we're going to make, is also a function of x alone, is a function of x alone, same variable. Then what we can do, we can use the separation of variable method. We can move the terms around, but here it's with respect to x, so we don't need the partial derivative anymore, because we assume that I is a function of x. So that means we can simply replace the partial derivative by the regular derivatives. So that's what we do. So let's say, so if this is the case, then we can write this equation as di over I using the regular derivatives. So the other side is simply my minus nx over n then and dx. Okay, so what we do now is we just integrate this one with respect to, so it's just a regular derivatives now, so just integrate with respect to x. It's not partial derivatives anymore. So this side is simply going to be ln I, the other side is the integral of my minus nx over n dx. And then once you take use the exponential form, you're gonna get I, now it is just a function of x, so I can write ix, which is e to the integral of mx minus nx over n dx. So that is the formula for the integrating factor. So let's put in this in a box. Now what we do, since we know the integrating factor, we do the standard thing. We're going to multiply by the integrating factor both sides and then use the exact equation technique to do that. So after we get the integrating factor, we're going to go back and multiply. So so what we can do, multiply by I, multiplying by I, we're going to get Im dx plus in dy. According to the assumption, this is just an exact equation. Okay, so this is your new m, this is your new n, so but it's just one function. So then what we do, we're going to solve this exact equation, solve this exact, because we know that this is exact now according to the assumption, exact equation. Okay, so that's the idea. So we solve the exact equation and then we get the answer. So that's one case. So because we assume that the function is only a, we make two assumptions. The first assumption was we assume that I is a function of x only, and then we assume that mx, actually here there's a small typo. This is my, not mx. This is my. Good. My minus nx over n. So there's a like a way to remember this one. So how we can remember this? So you can see that what we normally do is, remember we check the y derivative of m. So it's the same thing. See mx, and then we check the x derivative of n, and then divide by n. So you remember mnn. So it is my nx n. That's how you remember this one. And the variable is what is in the middle, so x variable. So that's so everything you get from x in this case, what is in the middle. Okay, so let's talk about the second case. So what's the second case? So I'm going to call it type 2. I'm going to call it type 2. So what is type 2? Is if I and, remember, because we need both I and. Now in this case nx minus my, so we reverse the order and divided by m now. Okay, so whatever in the corner we divide. So if I and m are functions of y alone, functions of y alone, then what will happen? Then you can see that the ix term is 0. So ix term going to be 0, and so we're going to get a similar argument. So we have iy equal nx minus my over mi, and this gonna give you a similar expression. So this gonna be iy now. So iy, which is integrating iy e to the same thing nx minus my over m dy now. So that is the new I in this case, so we're gonna put that also inside the box. Now how to remember this one? So there's a similar way to remember this one. Now what will happen, this is nx my m, so it is nmm, and what is the variable? Variable is what is in the middle, so the y variable. So y variable function, the previous one is a x variable function, the previous one is m n n, this one n m m, so like that. Okay, so and then after we do that, the same idea, so we're going to consider as before, we are going to consider the equation I m dx plus I n dy equal to 0, and then we're going to solve this. We're going to solve this exact equation. Solve this exact equation. So same idea. So only difference is here we get the integrating factor using a slightly different formula, and also you can see that when you do the integrating factor, in one you divide by n, and in the other one you divide by m. And how you remember that? That's always the last term. So it is m n n n m m, like that. Okay, so let's have a small note also, just to go with this. So I'm going to say a note, and theory is over. Now we can do one more example. So so the process doesn't work. The process does not work. The process doesn't work if we can say none of my minus nx over n or nx minus my over m are functions of one variable. So it's very important, are functions of one variable. If they are not function of one variable, we cannot do this. And so so in that case, so in general this equation mxy dx and xy dy equals 0 may not be solved, may not be able to solve, may not be able to solve. So that's what happened in general, okay, because you need to see that those things has to happen that way, because this mx minus nx over n is a single variable function, or nx minus my over m is a function of y. I mean that doesn't happen in general. So let's look at a just one example just to see how things going on. So example 1, solve, let's say solve xy dx plus 2x squared 3y squared minus 1 dy equals 0. So let's look at this problem, and then in this case you can see this is the m function and this is the n function. Those are the two functions. So we know what to do now. So we consider those expressions. So the answer in this case my which is x, nx which is 4x. So then you can see that my does not equal to nx. So that means not exact. So we see that. That's always a good idea to check whether it's exact, because if it's exact, you don't want to do this. So since it's not exact, what we're going to do, we're going to consider those two expressions. So we're going to consider my minus nx over n. So if you consider that, it is x minus 4x over 2x squared plus 3y squared minus 1. And you can see that you can simplify this a little bit. You can say it is 3x over 2x squared plus 3y squared minus 1, and it's very clear that this is not a single variable function. So not a single variable, it's not a single variable function. So that means this we cannot do, it didn't work. Let's look at the other one. But you can see that if we do nx minus my over m, if you do that, then you're going to get 4x minus x over xy. This nicely simplifies and you end up getting this 3 over y. So you can see there's a function of y alone. So function of y only. So since this is a function of y only, what we can do is we can use the second formula to find the independent factor now with respect to y, because it's a y function. So let's do that. So so that means we can calculate iy. So iy equal e to the nx my over m dy. So if you plug in here, you're going to get e to the 3 over y dy. This is very easy to integrate. It is 3 e to the 3 ln y. If you bring 3 inside, this can be y to the 3. So we have done this simplification before. Okay, now what we're going to do, we're going to multiply, that's the integrating factor. We're going to multiply by that the whole equation. So multiplying the differential equation by I equal y to the cube. So if you multiply by that, the original equation, you're going to get x y to the 4th dx plus 2x squared y3 plus 3y to the 5th minus y to the 3rd dx, dy equals 0. And see, we know that this is exact depending due to the way we form this. So that means we know that there is a function f such that this part is da by f over da by x and this part is da by f over da by y. So we can do the shortcut method now to find the solution for this. So we're going to do the shortcut method. So according to the shortcut method, what happened, we're going to set this equal to da by f over da by x, which is x y to the 4th. Now what we're going to do, we're going to integrate this with respect to x. Integrate with respect to x. Integrate with respect to x. So we're going to get f x y equal xy equals, if you integrate with respect to x, what are you going to get? 1/2 x squared y to the 4th, and we are not going to write the constant, we don't need that in this method. And then we do da by f over da by y, which is equal to the other term. So it is 2x squared y3 plus 3y to the 5th minus y third. We're going to integrate this one with respect to y. If you integrate this one with respect to y, what's going to happen? You're going to get from the first term you're going to get divide by 4, that means you're going to get 1/2 x squared y to the 4th plus divide by 6, that means 1/2 y to the 6th, and then minus 1/4 y to the 4th, and we are not going to add constants, we just leave it like that. Okay, now what we're going to do, we're going to look for the common term. So you can see this is the common term, and then this is the uncommon term. So we're going to write them in one expression. So that means your final answer is we can say fxy equal, we write the common term first, 1/4 x squared y⁴ plus 1/2 y to the 6th minus 1/4 y to the 4th. We set this equal to a constant, and then the solution is, what we can do is we can actually multiply this whole expression by 4. Actually not 1/4. Yeah, I think we made a mistake here because we divide by 4, so this can be 1/2. So 1/2. So I'm going to write it again. So this is 1/2 and 1/2. Okay, so 1/2. Now we're going to multiply the whole equation by 4. So when you multiply the whole equation by 4, you end up getting 2x squared y⁴ plus 2y⁵ minus y⁴. We still use the same concept. Actually it's a 4c, but this is fine. So that's a so that's going to give you y as an implicit solution. So that's how we do it. So you can see that this process is not that difficult, but there are some steps here. Okay, so let's write the summary like what we did. So that's it. So that's the whole problem. So this is going to give you the solution as an implicit function. Okay, so so in summary, so we're going to solve mxy dx plus nxy dy equals 0. So you can say in summary, can be solved as an exact equation, using an integrating factor, I x y given by, first, if my minus nx over n is a function of x alone, it's going to be a function of I. So it's ix equal e to the my nx over n dx. This we gonna remember as my nx n. Now the second case, if nx my over m is a function of y alone, we can write this one as y equal e to the nx my over m dy. It's a function of y. And then what we're going to do after we find this, we're going to solve the exact equation, im dx plus in dy as we did before, and which is exact. Okay, so that's the kind of summary and how we're gonna do. And then you can also remember the pattern of the expression, and here it is nx my m, so it is mnn or nmm, and then also it's always the variable in the middle, so it is this x is a function of x, is a function of y. Okay, so that's a summary, and then you can try these two problems for just to verify or make sure that you remember the technique, and you're going to see the answers to these in the description. So this is xy dx plus x squared 2y plus y dy equals 0, and the other one is 10 minus 6y plus e to the minus 3x dx, and then let's put a minus sign here, minus 2 dy equal 0. Okay, so you can solve these two and check whether you have the right answer in the description. Thank you.